Have you heard of TGV glass substrates? With its exceptional high-frequency transmission and low signal loss, it's becoming a promising choice for next-generation packaging in high-speed modules like 5G, IoT, and automotive radar. But it's not as simple as it seems. Many engineers face challenges when implementing TGV, such as low yield, glass fragility, packaging damage, and mismatched thermal expansion coefficients, which can lead to interface delamination. So, what can be done? The key is to improve yield by identifying the root causes of failure. In this video, we'll guide you step by step to understand why TGV failures and how to analyze and resolve the issues. Hey everyone, welcome back to iST channel. I'm your host today, Amanda. To receive the latest news and professional insights about the semiconductor industry, make sure to subscribe so you won't miss any of our videos. Do you know what TGV glass substrate technology is? Simply put, it's about drilling tiny holes in a glass substrate and filling them with conductive metal, allowing electrical signals to quickly pass from one side of the glass to the other. It's like creating high-speed channels between chips, making signals faster, more stable, and with lower loss. According to market forecasts, the TGV technology market is expected to reach $2.5 billion by 2033, showing impressive growth potential. Major companies like Intel, Samsung, and NEG have already begun developing and trial-producing new packaging architectures for AI chips and high-speed modules. However, the industry faces challenges when implementing TGV technology, such as process yield, packaging mechanical strength, and material thermal mismatch. These issues directly affect reliability and can delay mass production timelines. Today, we've invited iST's expert, Bernie, to walk you through 4 steps to break down common failure issues in TGV packaging. Through real-world cases, we'll help you understand the risks and opportunities behind this technology.
Hi everyone, I'm Bernie. While TGV technology has huge potential, there are 2 major challenges often encountered during its development process. The first issue is yield and cost. Currently, drilling holes in glass still presents many challenges. Whether it's laser or chemical etching, there can be variations in hole size and surface roughness, affecting conductivity and the uniformity of metal filling. The real trouble comes with copper filling. If it's not done evenly, the hole resistance increases, and there's a risk of copper diffusion into the glass. Over time, this could lead to insulation degradation or even long-term failure. The second issue is mechanical strength and packaging stress. While glass's stiffness, it is inherently brittle, and even micro cracks can lead to electrical anomalies during packaging, testing, or actual use. Moreover, the thermal expansion coefficient of glass differs significantly from that of copper. Once thermal stress accumulates, interface delamination can occur, impacting overall reliability. In the early stages of technology implementation, every moment counts towards development progress. If TGV substrates encounter issues, it not only hampers reliability testing but also risks delaying mass production timelines. Next, we'll walk you through 4 steps to help you quickly identify potential problems and accurately mitigate risks during material selection, early implementation, or before mass production. Our first step is to perform accelerated aging tests, such as HAST or HTS, to simulate long-term usage in high-temperature and high-humidity environments. This helps accelerate the detection of potential issues like copper diffusion, interface delamination, or conduction anomalies. The test conditions can also be customized and tailored, and when combined with subsequent destructive analysis, it helps you quickly pinpoint the issues. What should you do if issues arise? Don't worry. We'll use tools like thermal EMI or OBERT for hotspot analysis to locate the defect. Then, we'll perform 2D plus 3D scans with high-resolution X-ray imaging. Without damaging the sample, we can check things like whether the copper filling is uniform and if there are any voids inside. For high aspect ratio TGV package structures, we can also zoom in on specific areas to give you a clear and detailed view. Once failure localization is complete, we'll choose the most suitable method for sectioning, such as X-section, PFIB, or cross-section polisha, to perform precise cross-sectioning and reveal the anomaly. Next, we enter the world of microscopic microscopy. We'll use SEM or TEM to observe the details of the via interface, and pair them with EDS and ELS element analysis to see how copper diffuses and its concentration distribution. This step is especially critical for detecting trace copper diffusion inside the glass and helps us build a complete failure mechanism model. Additionally, we can use EBSD to analyze grain size, orientation, grain boundary characteristics, and residual stress. This information can be directly fed back to process engineers to optimize yield and packaging quality. Based on its past experience with TGV failure analysis, the two most common causes of conduction failure are poor glass via quality and uneven copper fillet. The tiny vias in a TGV structure must be completely and evenly filled with copper to form a stable electrical path. Any issues during the glass etching process can result in conduction failure. If electroplating parameters are not properly set, it can lead to voids, incomplete filling, or fractures in the pillar structure, which further cause electrical anomalies and packaging failure. In this case, we first performed non-destructive testing on the customer's sample using 2D X-ray to localize the defect. After precise cross-sectioning and observing with SEM, we discovered significant voids in the copper filling, which caused some TGVs to fail to conduct or exhibit high resistance. We recommended the customer optimize the copper plating conditions by adjusting the plating time. As a result, the copper fill completeness and electrical consistency were successfully improved, leading to a noticeable increase in overall yield.
Although silicon interposers remain the mainstream choice due to their mature processes and good heat dissipation performance, with the rapid development of applications like AI accelerators, advanced communications, and millimeter wave radar, TGV glass substrates are gradually emerging as a highly strategic, next-generation substrate in advanced packaging. With advantages like low impedance, high-frequency transmission, and excellent insulation, TGV is becoming an increasingly important technology in the field. To successfully mass-produce this technology and improve its reliability, failure analysis will be a crucial step. We hope today's discussion helps you avoid some common pitfalls and serves as a valuable reference when implementing TGV and tackling packaging challenges. If you have any questions, feel free to email us or leave a message. To stay updated with the latest news, follow us on LinkedIn or Facebook. That's a wrap for today. See you. If you enjoyed our video, don't forget to like, subscribe, and hit the notification bell so you won't miss any updates.